Okay, we've used Hess's law to help us determine the net enthalpy change for a reaction that might be difficult to measure by using the enthalpies of various constituent reactions. But you may wonder, do I have to measure all of those constituent enthalpies? You know, if I want to determine the enthalpy for some reaction using Hess's law, do I have to measure all of those individual reaction enthalpies? And it turns out in many cases you don't, because of something that is known as the standard enthalpy of formation. This is defined as the enthalpy for the reaction that forms 1 mole of a compound in its standard state, whatever it is at normal room temperature and pressure, directly from its elements in their standard state. So an example here is the heat of formation for ethanol. So it's the heat for the reaction for the formation of ethanol directly from its constituent elements in their form. So carbon as an element is a solid. Hydrogen forms is in its elemental form is the diatomic gas. Oxygen in its elemental form is a diatomic gas as well. And we have just 1 mole of this. So even though I have a fractional coefficient here, I'm not going to get rid of that by multiplying everything by 2, because that would then be the reaction for the formation of 2 moles of C2H5OH. And the enthalpy for this reaction is negative 277.7 kilojoules, and that is now the heat of formation of that element, or not that element, that compound, ethanol, in its liquid state. Now, what's so useful about heats of formation is that many of them have been tabulated, so we can simply look them up in a table. One thing to note here, and this is crucial when we're using heats of formation, is that the heat of formation for an element in its elemental form is 0. That's the basic state for an element. So it takes no energy to make it in its most basic state. So the heat of formation for any element then is just 0 in its elemental form. Now, as I mentioned, many of these heats of formation have been tabulated for many compounds. And it's also been tabulated in multiple different phases. So if you look down here for water in the liquid phase versus water in the gas phase, we see a different enthalpy. And we noted that way back at the beginning when we were talking about enthalpy, that the phase does matter. And so here we see a different enthalpy of formation depending on the physical state of the compound. Now, how do you use heats of formation to calculate the change in enthalpy for a reaction? It's actually very simple. So let's just take this combustion reaction as an example. This is one we could certainly do in a bomb calorimeter. We could measure it, but the change in enthalpy for a reaction is simply the enthalpy of the products minus the enthalpy of the reactants. We've already talked about that previously. But the enthalpy of the products is simply the sum of the heats of formation, or enthalpies of formation, of the products, and the enthalpies of reaction are simply the sum of the enthalpies of formation of those reactants. And that is extremely useful because I can look up many of those values in a table. So if we take this particular example, I have the table I'd shown previously. If I look here, I see that carbon dioxide is listed as a gas. C3H8 is listed as a gas with its value, and water in the liquid state is listed here with its value. And so I can use these values directly. They may notice, well, oxygen's not listed anywhere. Well, oxygen won't be listed anywhere because it's in its elemental form. That means the heat of formation of any element in its elemental form is 0. So the heat of formation for oxygen here is 0. So I can take these values then and plug them in. So on the product side, it's going to be 3 moles. I have in the equation, I have 3 moles of CO2. So times the heat of formation in kilojoules per mole, that will get me the total amount of enthalpy coming from CO2. plus 4 times the heat of formation of water as a liquid, 4 moles of water times its heat of formation. And that is the enthalpy of the products. Now minus the enthalpy of the reactants, well, it's 1 mole of C3H8, so times its enthalpy of formation, plus 5 moles of oxygen, but its heat of formation is 0. So there's no contribution from that. Multiply this through and then subtract, and you come out with an enthalpy of reaction of negative 2.220 times 10 to the third kilojoules for this combustion reaction. What's wonderful about this is we didn't have to do any calorimetry. You simply had to go to a table, and there are many out there. There's this one in your textbook, but there's many others. Find the enthalpy of formation for the substances that are involved in your reaction, and then follow this process to determine the overall change in enthalpy for the reaction. So let's do a couple examples of this. So we're given the standard enthalpies of reaction for a couple of the different compounds here, and we're asked to find the overall net enthalpy change for of reaction for these two reactions. So let's just start with number 1. First thing to note is just that delta H of reaction is just going to be equal to the sum of the delta HF for the products minus the sum of delta HF of the reactants. Now, if I look here, so products are going to be nitrogen gas and water gas. Well, we're given the heat of formation of water, but we're not given the heat of formation of nitrogen. Well, if I look at that, nitrogen, that's a diatomic element. It's in its elemental form. So the heat of formation is going to be 0 for nitrogen gas. So here, what I can write is on the product side, we're going to have 0 from nitrogen plus 4, because we've got 4 moles, times, not divide, but times 4, should be 4 moles times negative 241.82 kilojoules, and it should be kilojoules per mole. Sorry for the slight typo. And then that value, that's the products. Now subtract from that value. On the reactant side, I've got N2O4, which I'm given. Then I've got hydrogen, but I'm not given any enthalpy for that. Well, that's again an element in its elemental form, that's 0. So we just have on the reactant side 9.66 times 1. So kilojoules per mole times 1 mole of it plus then 0 from the hydrogen. And if we do all of that through, then we can come out with a final answer 4 times negative 241.82, and then subtract 9.66 from that, and we come out with a final value of negative 976.94 kilojoules for this top reaction. Okay, now let's take a look at this bottom reaction. So here we're given none of these species are in their elemental form. We're given the heats of formation for all of them. So we simply plug them in, multiplying by the appropriate numbers. It's again products minus reactants. So delta H for reaction is going to be equal to, on the product side, Cu2O, that is listed as negative 170.7 times just 1, that would be kilojoules per mole times just 1, plus NO2 is listed as being positive 33.84. And then on the reactant side, we have 2 times CuO is negative 156.1 plus NO is just positive 90.37. And you take all of that through, delta H of reaction is going to be equal to negative 170.7 plus 33.84, and then subtract, in parentheses 2 times negative 156.1 plus 98.37, and we come out with positive 84.97 kilojoules for this reaction. Now, we may have to pay a little bit of attention to our decimal places here. It looks like a couple of these we only have 1 decimal place, so we're going to have to round to just 1 decimal place. So this would end up rounding to positive 85.0 kilojoules. And that's how we would use heats of formation to find or calculate the overall heat or enthalpy for a reaction.